Continue with about 45 minutes remaining. Alice and Bob takes turns playing a game, with Alice starting first. Initially, there's a number N on the chalkboard. On each player's turn, that player makes a move consisting of choosing, any X with this, and N modulo X must, so basically X divides into N, replacing the number N on the chalkboard with N minus X. Play optimally. How do you even play optimally here? Suppose N was 100. You want to choose 50? Then it's 50. And then it's 5, 20, 10, 10, 5, 2, and 1. Let's say you start with 128. Alice can choose 64, which means N will go to 64. Bob can do this. Alice can do this. Bob can do this. Alice can do this. Bob can do this. And Alice can do this. Which means, Alice will win. I guess anytime you get to 2, whoever plays 2 will lose. And but what if Bob were to do this, right? Now what can Alice do? Alice can do this. And then Bob will win. right? Bob can always force it to 3 here if it's 4. And if it's 3, then there's no other choice other than 2, right? Um, what about 8? 8, there's 4 and 2. And if we know that whoever picks 4 loses, picks 2 also loses, can we have like induction sort of a situation? Like what if it was doesn't matter, 5, right? Then you can't pick 5, right? Because then you have to do, so whoever has 5 also wins. Uh, so it's 6. All right. 6 says, so whoever has 3 wins, and then, obviously whoever has 1 wins. So the 6 lose, right? 6, you can choose, 2, in which case you would just win, and win. Right? Because you always just choose 2 and then force the other player to be at 4, in which case they lose. Or, I mean, you can, yeah, I mean, if you don't play optimally, you might choose, yeah, I mean, if you choose 2, um, if you choose 3, then you'd lose. But there's always a path to win here, so wins. Um, so let's revert these, right? Loses false, because Alice goes first, wins true, loses false, wins true, loses false. So if 2, I get to win because I do this move. If I'm 3, uh, if N is 3 and Alice plays first, they'll lose because, so false. If it's 4, then you can win because you can force the other player to be 3. If you're 5, then you have no choice but to play 1. And then then the other person wins. 6, you have some choices. And basically, that's why this number is so low, because you have to build a board. So 6, you basically scan it and say, well, if I can pick a number where the other, actually, here I must choose 1, so the other player wins. Here, so whatever, yeah, so this one is a win. True. Okay. And the reason is because this player can pick 3, forcing the other player to lose. So basically, I scan this, and if there's anything in here that allows the other person to lose, then that means I win. But if there's nothing that I can choose scanning this, like modulo, like if I can't force the other person to lose, then what? Does that mean I automatically lose? So for example, this Yeah, because it's either win or lose, right? So if every choice I can't find a spot where the other person loses, that means they win. And if they win, that means I lose. And then this kind of induction sort of goes on. Um, so, uh, I can say false, true, uh, false, true, false, true. Because that's the ones I solved for. So if n is um, less than or equal to 6, then just return starting, I'll just call this a seed of um, so n minus 1. So n is 1 to 1,000. So this is 1, this is 6. So 6 minus 1 is 5. Um, uh, for I in range, no. Yeah. Um, so like seed would have some sort of this kind of thing. For um, right, so the number you would check is actually going to be I plus 1 to check, because actually we want to start 1, but you can also just say like this, to be honest, for a little bit cleanerness, if that's a word. So num to check, and then so c num to check minus 1. So this you just basically want to scan and then kind of see, yeah. So first is num to check is n. If num to check is even eligible, then we check this, and basically I'm looking for a win. So what I say, so if I can't force the other player to lose, so if I go, I'm 6, and then I'm like, I pick 3, and the other person is false, then that means I'm true. And if I can't find anything, so if I can't find any falses, then I am false. So for every number I'm going to reset this check to false. And then I'm just going to scan on the numbers. If it's divisible, I'm just going to go ahead and say, well, check is equals to this. And if actually, yeah, basically, if I'm going to force other player to lose, then c dot append true. Okay. And then if after, and then I'll just and then let's break out of this and then work on the next number. But I've never set this check flag to true. So if not check, probably flag is better, but yeah. If not flag, which means I didn't set it to true, then c dot pen false. Print seed, and then so let's say n was 8, then sorry, 7, then you would include 7, exclude 8, which is 7. If this was like 100, then it go to 7 to 100 for num. And then so you always just return like that. I'm also curious to print this seed, and then I run code. Let's try. um, so 7. So Alice goes first, and it's like 7. Then I could pick 1. Then that means the other person wins. Oh, I see. because this is num to check. And so let's say I pick 1. This would pick, 0, but actually I want to pick n minus this. So in this case, it'd be equivalent to going to 6, which is 5. So 7 minus 1, minus 1 is 5. So let's try it again. Still true, huh? So num to check is 1. Oh, equals 0. Okay. About 8. 8, there's so I built this correctly, and then num to check equals 0. So n is 8 minus 1 is 6. 6 equals false. I should have appended true and break. So I'm very curious. What's happening here? Oh. It's num instead of n because right, we're sweeping it up to the thing. Wait a second. Yeah, for the same reason, because they're just building up n. And let's see these indexing issues. Okay, finished. Um, yeah, I guess, yeah, I don't know why it said they're both easy, but probably not. Anyway, I think that's it for this one, and I'll probably wrap up for today. I will see you in the next one.